All right. Thanks for coming out to this week's discussion hour. This is the last one of the semester and it's a PhD talk, so this is exciting. Today we have Wei Wei, who is a PhD candidate here at UTIG. Her research focuses on ice-ocean interaction in Antarctica, and she's part of UTIG's Polar and Planetary Group. Before joining UTIG, she obtained a bachelor's in science in applied geophysics from Jinlin University, and then a master's in science in the Geosciences at the University of Texas at Dallas. And then one thing I want to mention before Wei Wei gives her talk is that this is a PhD talk. And so one thing that's really helpful for PhD students is getting feedback on their talks. So I will put the link into the chat and also send it out in the email later on, but be sure you fill it out. It's great feedback, and she'll also be entered into the contest for the best PhD talk of the semester. So yeah. With that, take it away, Wei Wei.
Thank you, Naoma, for the introduction. And also, thanks everyone for being here today. My name is Wei Wei, and I'm working with the Polar and the Planetary Group here at UTIG. Today, I will talk about some ice-ocean interaction process in Antarctic with focus on two factors, the bathymetry and the subglacial discharges, and along with case studies from two ice shelves, namely Gas Ice Shelf and the West Ice Shelf. Before delving into my science project, let's do an Ice Shelf 101 first. Here's a map of Antarctic surrounding by the Southern Ocean. The color in gray is the grounded ice that sits on the bedrock. Glaciers on the edge of Antarctic flow like slow rivers towards the coast. When this ice flow reaches the ocean, the ice starts to float. This huge, thick, floating tongue of ice is called the ice shelf, which is indicated by the white area. The magenta line is called grounding line, and the grounding line is where the ice starts to float. Here's a typical ice shelf profile in the lower right. The area between the ice bottom and the bedrock is the ice cavity. It is where the ice and ocean interacts with each other. The photo in the upper right shows what an ice shelf looks like. Since the ice shelf is already floating in the ocean, the melting of an ice shelf itself won't contribute significantly to sea level potential. And the ice shelf matters to sea level because it buttresses the ice sheet. If the ice shelf has any changes in its geometry, this buttressing effect will be reduced. Then more ice will flow into the ocean, the sea level will rise. So the buttressing effect from the ice shelf can be reduced by two mechanisms. The first one is called marine ice sheet instability, which is initiated by changes on ocean circulations or atmospheric drivers. In particular, the warmer ocean water moves towards the ice fronts and ice shelf grounding line can cause increased melting at the ice-ocean interface. We'll talk more about this later. So basically, unstable grounding line retreat may happen, especially when the bed deepens inland. More recently, the hypothesis of marine ice cliff instability has emerged, and proposing that ice cliffs become unstable and collapse if the ice cliff is higher than 90 meters above sea level, which can facilitate the rapid retreat of ice sheets. The cliff instability is favored by a process called hydrofracturing, which is due to the increase of water pressure in surface crevices. These surface crevices may get wider and deeper, and eventually the and eventually the ice shelf will collapse, thus reducing the ice shelf's buttressing. So either mechanism shows the geometry changes in the ice shelves can affect the ice sheet's stability. The geometry change in ice shelves take place mainly in two ways, either carving icebergs from ice shelf front or by basal melting from below. My study mainly focused the process related with the basal melting. The figures on the left is the ice loss from Antarctic from 2002 to 2020, measured by the GRACE mission. The red indicates where the mass is decreasing, and the figure on the right is a map of basal melt rates. The color in the darker red is areas where there are very high basal melt rates. So the areas that the black arrows indicate on both figures show strong correlation between where the grounded ice is decreasing and where the ice shelf is losing mass by the high basal melting. Such high basal melt rates is believed to be driven by the warm ocean water incursion into the ice shelf cavities. This warm water is called circumpolar deep water. I'll refer it to CDW in the rest of this talk. The right figure shows the CDW provides a reservoir of ocean heat surrounding Antarctic. The warmer color is the temperature above the pressure freezing point, and the blue is the temperature below the pressure freezing point. Just for contrast, the surface water temperature is shown on the left, just to remind you that the surface water is still very cold. So this CDW is sourced in deep ocean beyond the continental shelf break, and it is a warm, salty blend of water masses, including North Atlantic deep water and Antarctic bottom water. Then CDW is transported clockwise around the continent in the Antarctic circumpolar current. The southern boundary of this current is located close to the Amazon Sea region, West Antarctic, and also below 60 and 150 degrees east in the East Antarctic, which are defined by the two orange boxes. Gas shelf and west shelf, and which I'm going to mainly talk about today, is located in the two regions respectively. You may wonder how CDW can reach into ice shelf cavity. At places that wind can cause surface water to diverge, warm deep water, which is indicated by the red arrow in the map, can actually upwell and surmount the continental shelf. Then the troughs on the bathymetry can form a pathway for the warm ocean water to cross the intercontinental shelf and reach the ice shelf cavity and melt the ice shelf from below. This is a sketch shows the active interaction between ice shelf and the ocean. Ice can either melt off from the ice bottom or the ocean water can freeze to the base. And the melting and freezing are driven by the depression of freezing point of seawater with increasing pressure. Melt is often focused near the deep grounding line, where water reaches to the ice shelf base. It is far below sea level and at a much higher pressure, so water there can still be in the liquid status at temperature down to below about -2 Celsius degree. and ice starts melting as soon as the temperature reach above this pressure melting point. Basal melting can be characterized by three modes. The first occurs where dense, high salinity shelf water is formed near the ice shelf front during winter sea ice growth. The second mode is due to the incursion of circumpolar deep water into the ice shelf cavity. And the third mode is due to tidal and wind-induced mixing near the ice shelf edge. And the degree of melting that occurs in the ice shelf cavities can be broadly classified into two major types. Low melting in cold water cavities and high melting in warm water cavities, with the latter having modified CDW directly in contact with the boundary layer at the ice shelf bottom, and the former is not. The first and the third mode is active for ice shelves with cold water cavities. The second dominates in warm water cavity. Also, there is an active hydrological system underneath the ice sheet. Here's a figure shows that subglacial water flux distribution. This water can move from the interior of the ice sheet towards the coast. And when this water crosses grounding line and is discharged into the ice cavity, it will add buoyancy to the meltwater plume and enhance the basal melt rate. The profile in the upper right shows basal channels are even always coincident with the output locations of subglacial discharges. In Greenland, this subglacial discharge can be the principal control on the basal melt rate. For example, in the left figure, pink dots are the locations of subglacial discharge outlets, and also extensive melt are associated with these small discharge outlets. In the right figure, in Alaska, it was observed that melt rates increase with about 1/3 power of the subglacial water flux. However, the role of subglacial discharge play in control the basal melt rate in Antarctic is still poorly explored. So for the next 15 minutes also, I'll talk about some results from Gaza Shelf in West Antarctic. So let's look at the location of Gaza Shelf first. The green lines is the outline of Gats. It is about 500 kilometers long, 30 to 100 kilometers wide along the Amundsen Sea sector, and it is the ninth largest ice shelf in Antarctic. I'm originally interested in gas because it is the largest meltwater source from Antarctic to Southern Ocean. It produces about 144 gigatons of fresh water per year and has an average melt rate of 4 meters per year. The influx of fresh water is also known to influence the ocean circulation and biological productivity. In the histograms, the vertical axis is the ice draft, the horizontal is the meltwater flux. Among all the large ice shelves, Gats is experiencing very excessive melt rate at depths among all the warm water cavities. The ice shelf thinning in Amundsen Sea embayment has been attributed to the circumpolar deep water intrusion. What you see here on the right is a thermal profile from ocean observation from Pie Island to Gats. And some of the gray bars are islands and peninsula. The color is ocean water temperature above the pressure freezing point. And we can see CPW is intruding at shelves in Amazon Sea embayment. And if we look at the ship track symmetry on the left figure, for the open Amazon Sea, the outstanding features are these deep troughs that act as shelf front. For the gas region, the eastern Dawson gas trough split up to feed both the Dawson and the gas as shelf. On the western gas, there's also troughs lies outside these ice rises. During the past ice ages, these deep troughs are carved by the paleo ice streams into the continental shelf. And they are the primary pathways for the ocean water to access the ice shelf from. However, whether these troughs are continuous through the ice shelf cavity, we need to know the bathymetry of the water cavity. To understand the potential pathway for warm ocean water to enter into the gas cavity, we conducted a bathymetric survey using a ship-based gravimeter-equipped helicopter as part of a collaboration between UTIG and the Korea Polar Research Institute. What's on here are some photos that shows the gravity data acquisition platform that is based on the icebreaker Aram. And this is a helicopter AS-350 loaded with the gravimeter, which is trapped in this red cage. And these are the GT1A's power electronics and GPS receivers. The survey covers area between Dean Island and the Sable Islands, located in the west of Ghats, as shown in these green lines. They cross existing coastal parallel operational ice bridge lines, which is here shown in blue lines. The gravimetry from the helicopter platform can achieve a higher resolution of 3 kilometers, which is higher than the conventional fixed wing surveys, which has a resolution about 4.9 kilometers. Because the helicopter has a lower flying speed, so it has a higher resolution in the gravity data. Actually, this is the first practical use of gravity observation from a helicopter operating from an icebreaker. So with the addition of the helicopter lines, the quality of data is improved by providing more information in the potential deep trough locations in the West Ghats. The bathymetry is inferred from airborne gravity data inversion. You may wonder why we can use airborne gravity to infer the water rock interface under the floating ice. That's because the Earth's gravity field can change at different locations according to different topography and a different density distribution. Essentially, the greatest density contrast in floating ice area between air, water, ice, and rock. Therefore, the gravity data can be used for modeling the interface between these three elements. We use GMSYS profile modeling, which is developed by Geosciences. It is a 2D modeling method. Basically, what it does is to approximate the irregular geological model with a polygon, which has a multiple side, then calculate the gravity field to this polygon that best fits the observation data. The new bathymetry reveals deep troughs are continuous from inner continental shelf to beneath the ice shelf. In Western Ghats, we identify a 1,300-meter deep trough between Saipol Island and the Ding Island, which we refer to as Saipol-Ding Trough, SDT. In Eastern Ghats, we find a 1,200-meter deep trough between Duncan Peninsula and Wright Island, which we refer to as Duncan-Wright Trough, DWT. We previously see the ship track bathymetry shows that the Dawson gas trough on the inner continental shelf extends to the ice shelf front, and our results shows that DWT is the continuation of Dawson gas trough, providing a pathway for CDW to enter into the ice shelf cavity without obstruction. Similarly, SDT is a continuation of West gas trough. DWT and SDT are actually not fully connected, but they are separated by a bathymetric seal that rise to a depth at about 500 meters between the Saipol and the Kani Islands. So let's look at the profile XYZ, which sample along the SDT, the seal, and the DWT. In the bottom panel, the green and the blue lines are on the two sides is the thermal forcing as a function of depth from ocean CTD casts. We identify the yellow line as the thermocline depth, which is at about 500 meters. The top of the seal sits slightly below the 500-meter thermocline depth and may allow for exchange of warm CDW between eastern and western gas cavity. The top panel is a melt rate. Notice the melt rate looks relatively higher in the section YZ than the section XY. This is possible, as we can see from the bottom panel, the ice bottom from YZ is below the thermocline depth. So it's more clear also to see from the map of the melt rate. DWT region has a higher melt rate than SDT. These black dots marks where ice bottom elevation is greater than 500 meters, which is aligned, which is again the thermocline depth. So the Eastern Ghats region overall has deeper draft that allows the bottom of the ice soaks in the warm water. In the contrast, the base of ice shelf in the SDT sits in the relatively colder water because the ice bottom elevation is shallower than the thermocline depth. And this also has implication that the existence of troughs doesn't necessarily means that the melt rate will be very high over it. And this map also shows that the channelized melt rates pattern that is mainly focused near the grounding line. As we say, subglacial discharge has been shown to affect the melt rates in marine terminating glaciers in Greenland and Alaska. We explored the relationship between subglacial discharge and the melt rate. These blue lines are the subglacial discharge locations. The melt rate in this figure is defined as the melt rate difference, which is the observed satellite melt rate minus no discharge melt rate. This melt rate difference can tell us where melt rate is higher than expected, as shown in the red area. Channel A near Grant Island has the largest channelized relative discharge rate at about 5 meter-cube per second, while the channel outliers near the grounding line between Kani and the Duncan Peninsula has relatively discharge range between 1 and 2 meter cube per second. And these channel outlets and the relative discharge match up with ash shelf melt rates that are more than 10 meter per year. So just for comparison purpose, here's just a much better version figure, shows what I just described, the relationship between melt rate and subglacial discharge. It shows how nicely the channel outlet locations is lining up with the elevated areas of high melt rates. So last month, another gas paper just came out demonstrating that a number of glaciers in gas region has sped up coincident with the regions of high subglacial water fluxes, which again point out the importance of subglacial hydrological system to the stability of ice shelves. So let's switch gear a little bit from West Antarctic to East Antarctic. West Ice Shelf is one of the largest unsampled ice shelf in Antarctic and covers an area of more than 16,000 kilometers squared. It's located close to the continental shelf break, which is shown in the orange line. Making West naturally vulnerable to warm atmospheric and ocean heat delivery. However, the front of West is attached to the iceberg D15 and also with a large area of persistent sea ice, making it very difficult to measure the bathymetry surrounding and beneath the ice shelf. Also, public available bathymetric charts are interpolated over a vast area surrounding West, making it also difficult to interpret the routing of the CDW. West is an important ice shelf because it drains Leopold and Astrid coastal basin, which is named after the king and the queen from Belgium. This basin currently holds about 1 meter sea level potential. Also, a hydrological system has been proposed underneath the ice sheet near West. Subglacial water are likely being directed towards the I think my PowerPoint was terminated.
That's okay. We can take a moment for
Sure.
it to reopen.
Sure. Let me restart everything.
I hate when that happens.
Yeah. So can you see my screen?
I can.
Okay, great. So where am I? Yeah, so I'm talking about the hydrological system that has been proposed near West Shelf. So the subglacial water are very likely being directed from the interior towards the coast. And the lower right figure shows the underside of the ice shelf is possibly smoothed out by the subglacial discharges. So we also consider subglacial discharge as a factor to affect the melt rate in this region. This is the first study towards the West Shelf sensitivity to ocean changes and subglacial discharges. Airborne geophysical surveys of West were conducted to investigate the response of ice shelf basal melt rates to conditions in the underlying ocean and to understand how ice shelf melt is influenced by the discharge from that subglacial hydrological network. Here's a map of data that has been collected from the ice cap survey. For my study, I grabbed a subset from there, which covers the Leopold and Astrid coast, the West Ice Shelf, and the Summit region covered the inner continental shelf. So the data was collected by the two World War II era aircrafts. They are already more than 70 years old. Airplane on the left is called Snow Eagle GCX, and the right one is JKB. Taking the JKB platform, for example, it has equipment that include radar sounder under two wings, gravimeters, magnetometer, GPS, LiDAR, and the camera. And the GT2A is the same brand gravimeter we've seen from the helicopter survey. So from each flight, simultaneous geophysical data was collected. I mainly used the gravity, magnetics, and the bed depth derived from radar data in this project. Then I applied the similar 2D gravity inversion approach from GATS to WEST using radar and the magnetics as constraints. So the inferred bathymetry for WEST is shown on the left. On the right is a comparison to the public data sets, which shows featureless bathymetry near WEST, as you can see from the top panel. The lower panel is a difference between the new and the old bathymetry from Batmachine and the Batmap 2. Blue here means deeper and red means shallow. So compared with this new bathymetry, West Shelf is overall deeper than previously thought. We also look at the vertical distribution of water masses near the ice shelf that is compared to the vertical distribution of melt rates and the total areas of ice shelf itself. The vertical axis is basal depth from the second subplot, which is the melt rate as a function of basal depth. There's a significant bump in the depth around 675 meter, which is marked by the red line, whereas above that depth, actually the melt rate is relatively lower and constant at about 1 meter per year. The figure D, the fourth figure, is the thermal forcing plot from 375 sail divers within 5K of the ice shelf. The locations of these CTD casts are green dots from west side and the yellow dots from the east side. Oh, actually, these CTD casts are brought to you by the sail divers. Back to the thermal forcing plot, it shows a weakly stratified water column without a distinct thermal column depth. And we'll talk more about this later. If we look at the temperature salinity diagram, it shows mainly cold water mass with conservative temperature below minus 1.7 Celsius degree near the calving front of West. Expanding the search for CDW, we also look at all the CDD casts near West. The color is the distance from the closest ice. So yellow means very far away, and and blue is much closer. Among of the about 400 CTD casts that were collected, there is no direct evidence of CDW within 50 kilometers. The closest CDW from the CTD casts has a distance about 52 kilometers to the ice shelf front. One possible explanation for the lack of CDW near west coming front could be that warm, dense water mass is blocked by the bathymetric heights around here. So if we look at the transect XX prime, we find that only cold water reaches a nearby ice shelf region, and the CDW is blocked away at about 200 kilometers. Going back one more time to the vertical profiles to understand the bump in the melt rate, we investigate the melt rate area that exceed the melt rate that would be expected from their depth. Again, the subglacial discharge lines up well with the elevated melt rate area. Subglacial discharge explains the depth, the bump in the depth average melt rates below that 600-meter depth. And this is also supported by the relatively linear increasing in the thermal forcing profile as a function of depth. And with that, it couldn't create a distinct bump in melt rate at a given depth. So I hope I have convinced you that the bathymetry and the subglacial discharges are important to understand ocean forcing and subglacial discharge forcing on the mass loss of Antarctic ice shelves. And also the control from subglacial discharge on the ice shelf basal melting are likely widespread around Antarctic. Also, this new data will be important to guide future surveys and help interpret recent and past changes in ice shelf and inform future modeling work of ocean circulation and ice sheet to better predict the future impact from ice shelves. The last but not the least conclusion, the science is never possible without the great collaborators. There are people that either collaborate on the science project, offer great advice to the research, or help collect the data in my project. I learned a lot from working with them, and just a big thank you to all of them. Oh, thanks also to Naoma and Enren to host my talk. I'm happy to discuss or answer any questions.
So anyone with questions can go ahead and unmute themselves and ask, or you can also type it in the chat, or you can raise your hand. Kind of anything goes.
It's awfully quiet out there. Wei Wei, can you hear me?
Yes, I can hear you.
Hi, this is Don. We were looking on that eastern side of west. There's a suspicious low spot. To the I can't remember the name of the island in the shelf break. I did have a chance to talk to Jamin about that, and he thinks there might be MCDW leaking in there. Have you talked to him about that?
Yeah, we discussed about it as well. So So we didn't exclude the existence of any MCTW or CTW underneath the ash rock cavity. We just didn't find direct evidence from the seal divers.
Yeah, it sure isn't in those CTD casts, but there aren't that many of them out there. So, and I have another question. Is that okay?
Sure.
Yeah, the most suspicious thing right now is the water channel routing for the onshore part. Which topography ultimately got used for that water routing now? Because now we can actually see the melt rates and the topography and the water routing all at once. And interestingly, that one over on the east side of West doesn't seem to have a big impact. What do you think about the accuracy of the topography and the accuracy of the water routing going from east to west?
Yes, so the topography for this subglacial water routing is from Bathymetric. So, and I think which also provide information like the topography over the grounded ice, where we can see the deep troughs. Here. Yeah, we can see the deep troughs near the grounding line of west, and also the subglacial meltwater estimate is for this method. I assume the bed water pressure is equal to the overburden pressure of the ash sheet. So this gives like an first order approximation of what the subglacial routing will look like.
Yeah, and could you go back to that topography one more time, and we can have a look, because there are lots of people desperately trying to infer canyonized topography, onshore. And I'm trying to look at, it looks like the bed machine resolution is at best about 15 or 20 kilometers. So there's a chance that water could be leaking through there at a resolution that bed machine doesn't see. So it's going to be interesting to reconcile. I think that's Schwei's problem right now, isn't it? You're not having to deal with that. Okay, we got a thumbs up that it's Schwei's problem. So I'll drop it with that one.
Okay.
Well, I have a question too, but I don't know if Patrick maybe was first. But it's tied to Don's question with the water routing. I was wondering, like on the map,
Sure.
like if you go one more slide, like Don mentioned too, there were like spots where there's high melt rates.
Sure.
But where like the water routing doesn't like go there. I was wondering, did you do like a sensitivity test where you like make like random errors in the bed elevation and the surface topography and run it like 1,000 times and see if like those routes might deviate in some instances, like where the bed elevation changed just a little bit and would then go towards those basal melt, like those high basal melt areas?
Sure. So I didn't do the sensitivity analysis, and according to the developer of this water routing package, roughly if you change the bed topography, it may change like about 10% difference just from the just from the looking of the figure. So the difference will be mainly in the visual perspective.
Yeah. Yeah. If you want to, like,
Yeah,
like
that
I could
sounds
help
great.
you try look at that. I did that for like Seven Ice Cap, and it was like interesting to see the changes.
Yeah, hi, Wei. Nice.
Hi, Patrick.
I was wondering, you showed this the results from the how gas continues to the freshwater flux to the ocean. Do you have a sense of how much freshwater flux from the ice shelf, how much that is compared to just the net mass loss, for example, regionally to the ocean, right? Which are different things, right? The net mass loss is just the melting accumulation minus melting, but then the on the grounded part of the ice, it's estimated. But oftentimes people forget that the freshwater flux can be much larger. Do you have a sense of how much of that, how big that is?
So Patrick, are you asking the rough number of that meltwater from the ice shelf, or from the grounded ice?
No, just from the floating ice. So really just the freshwater flux. So basically whatever is melting, but no.
Sure.
Yeah.
Yeah. So I happen to have a supplementary slide where it shows the meltwater production on a yearly base from 1994
Oh, nice.
to 28. So definitely we can see the ocean forcing is variable in gas region. So I think the 144 number is just taking an average from all this number here. Then that's how that was calculated.
And where is that number derived from? How is that number?
Yeah, so that number was basically just taking an average of all the meltwater productions from this about like 20 years.
Right, but how do you know, where does that number, is that thinning from altimetry or reanalysis or where
Yes. So like the figure here is from satellite observation. And also that number has also been validated for some ocean modeling results. Like, for example, like Tosh's setup also validated that. I think he got like 130 also gigatons of fresh water at GATS.
Okay, great. Yeah, thanks. Thank you.
Thank you. Do you have a question, Natalie?
Oh, yeah, sorry. So I was curious for the like negative melt rates. Is that just referring to basal freeze-on then?
Yes, so for the observed melt rate, so I'm trying to find a figure. So the blue area is basically melt rate below 0. Is this what you were asking?
Exactly, yeah. So I'm just curious, like it seems kind of high in some places if it's referencing like freeze-on. But I don't know. Is that what it's indicating?
Yeah. Yeah, and also from the radiogram, where I don't have it here today, but it also shows the from the radiogram that go over these islands here, we don't see the bottom of the island because, for example, for gas region from the old radiograms, I can see the bottom of the islands, but for here, I didn't see the bottom. And Duncan mentioned that this might be something you might be interested to investigate because the ice seems to be warmer here in this region.
That's really cool.
Any other questions?
Yeah, let me go ahead and just sew that up for, for Natalie, that since I saw the same thing, can you talk about how the circulation in that east part of gets? I mean, I have a picture in my head and we talked about it, but for Natalie's benefit in particular, it looks like there's a bunch of water, go ahead and leave that last one up, the melt rate one. I'm sorry, I didn't mean Getz, I meant West, the one that we were looking at. Yeah, that one. Yeah, if you go over to the east side, you see all that discharge and a bunch of melt. But then it looks like the coastal current is sweeping that fresh water under the ice shelf. And if there isn't any MCDW coming in, then, like you say, it's going to be mostly stratified. And the farther away you get from the source of that fresh water, the more freezing, which is exactly what it says. But what I'm interested in is why there's that line up the middle, and it's melting out towards the continental shelf and then freezing in towards the grounding line. That's beyond my model in my head. Have you thought about that, Wei Wei?
So Don, are you asking like this blue
Yeah,
area?
that line right in the middle where it's freezing on the grounding line side and melting on the shelf side. Is that what you know more about the circulation of the cavity than me, and Patrick's out there. Is that what we'd expect if there was no NCDW leaking in?
Well, I think we don't exclude any existence of MCDW or CDW in West. So our reported existence of MCDW or CDW is based on all the CDD casts from WOA and all the seals and all the CDD casts from seal divers. And these black dots, yellow dots, the green dots, yellow dots are all the CDD cast locations. And there is still a gap here that where the seal divers seems not like to travel. So, I mean, I just want to mention there's still like a data gap here where it might provide more information.
Yeah, anyway, clearly there's a lot of work to do in there. So we need a circulation model for West. I'm done.
Sure, thank you.
Natalie, your hand is raised. Is that from your last question or do you have an additional one?
No, it was the last one. Sorry.
Yeah, no problem. We do have time for any other questions if there are any. All right. Well, thanks so much for coming out. This was the last discussion hour of the semester, so we'll be back in the fall. Thanks very much to Wei Wei. Congratulations on your PhD talk. Please fill out the evaluation form and I'll send it out again with the recording of the talk. But for now, take care.
It's a bunch.